Electrochemistry is chemistry that involves the exchange of free charge, exchange of electrons, rather than just how they are shared. Electrochemistry differs from thermochemistry in that we can apply an electric potential to push electrons around to make the reaction go either in the forward or reverse direction. As always, there are conservation laws. Not only do we have to conserve energy and mass, just as in thermochemistry, we also have to conserve charge. In electrochemistry, if there are 12 positive charges on the left-hand side, there better be 12 positive charges on the right-hand side. Let's define the basic processes in electrochemistry. Remember, if a reaction is going to balance charge, something is going to have to donate an electron, and another species is going to have to accept an electron. Oxidation is the removal of electrons from a species. The electron is negatively charged, so losing an electron increases the oxidation state of the donor. Reduction is the addition of electrons to a species. Losing an electron reduces the oxidation state of the acceptor. There are two types of electrochemical cells that we specify, depending on whether the reaction is spontaneous or not. In a galvanic cell, the electrochemical reaction is spontaneous and leads to the production of electricity. An electrolytic cell is an electrochemical cell in which a non-spontaneous reaction is driven by an external source of current. Electrons are negatively charged and flow from low potential, from the minus, to high potential, to the plus. The spontaneous direction of flow is for electrons to move from a more negative electrode to the more positive electrode. In a galvanic cell, you have spontaneous electron transfer. Electrons move from the anode to the cathode, to the more positive electrode, and that's the spontaneous direction. In an electrolytic cell, there's no reaction at first. It's not spontaneous. The cathode must be at a more negative potential. But if we apply a bias, we can move the cathode down to a more positive potential, and then electron transfer can occur from the anode to the cathode. Note this means that the sign of the anode and cathode changes depending on whether the cell is electrolytic or galvanic, but the direction of change is always the same, from the anode to the cathode. In a galvanic cell, the spontaneous reaction occurs and the potentiostat just measures the voltage and current. In an electrolytic cell, the potentiostat applies a bias to the electrodes and forces the electrochemical reaction to run in a particular direction. A redox reaction is formed by combining two half reactions. The oxidizing agent, or oxidant, is an electron acceptor. The reducing agent, or reductant, is an electron donor. The reduced and oxidized species form a half reaction known as a redox couple. The couple is written red, ox/red, and it corresponds to this reaction. The oxidized species takes on Z electrons to form the reduced species. Z is known as the electron number of the electrochemical reaction. It's also sometimes called the valence. Now let's consider a reaction of, say, O2, the reduction of O2 with protons. And we have to couple this reduction with an oxidation. Let's choose the oxidation of H2. However, we need to balance electrons, and to balance electrons, we have to multiply the oxidation by 2. We have to multiply every species by 2 in order to get the electrons to balance. When half reactions are added to balance the number of electrons lost, with the number of electrons gained, the overall reaction will be balanced. Note that electrons appear as reactants and products in half reactions, but they do not appear as reactants or products in balanced overall chemical reactions. Now, why does the electron hop? Well, chemical systems always evolve to lower their Gibbs energy. That defines the way forward. So, electron transfer occurs if it lowers the Gibbs energy of the system to move an electron from an occupied orbital to a species that has an unoccupied orbital that lowers that process, has to lower the Gibbs energy. Because an electron has a negative charge, the sign of the electrical potential scale is the opposite to that of the energy scale. Electrons move spontaneously from high energy states to lower energy states, from states at some electrical potential to states with more positive electrical potential. Now let's consider the band structure of our electrode. We could have either a metal or a semiconductor. Electron transfer with a metal happens primarily at the Fermi energy. That's the highest chemical potential of electrons in the metal. Electron transfer in a semiconductor is more complex. There aren't any electrons at the Fermi energy in an ideal semiconductor. So electron transfer out of the semiconductor can occur at the top of the valence band, or electron transfer into the semiconductor can occur at the bottom of the conduction band. But let's concentrate on the metal. If a positive potential is applied to the metal, the electrochemical potential of the electrons moves down. If the potential is made positive enough, an electron will be transferred from an occupied orbital in the solution phase species to the metal. If the electrode is biased with a negative potential, then when this potential is negative enough, it will meet or exceed the energy of an unoccupied orbital in the solution phase species, and we can get electron transfer from the electrode to the solution phase species. Note that the direction of the current flow can be changed. Which species is the donor, which is the acceptor, can be changed based upon the applied electrical potential. And we call that potential the overpotential. The overpotential is 0 when the system is at equilibrium. There's no net current because the anodic current and the cathodic current balance at equilibrium. Chemistry doesn't stop at equilibrium, it's just that the rates of forward and reverse reactions are the same. But if we apply a negative overpotential, we can bias the system toward the cathodic current, and if we bias it at a positive potential, we can make the anodic current flow. So, how does electron transfer occur heterogeneously at a solution solid electrode interface? A solvated species moves toward the surface. It will diffuse toward the surface, and then it will become either non-specifically or specifically absorbed. Specific absorption is when the adsorbate directly contacts the surface of the electrode. Non-specific absorption is when the solvation shell stays intact. Once the species is stuck to the surface, adsorbed on it, electron transfer occurs in the absorbed phase. And then, after electron transfer, there may be some other chemical steps that occur, and eventually this adsorbed species desorbs back into solution. That is how heterogeneous electron transfer occurs at the electrode solution interface.